All human civilizations have thought very hard about units. If you go to the shops and you want to buy a certain amount of a material, whether it's a weight or whether it's a volume, you are going to be using a particular unit. If you want to buy an area of land, you will want to know what the area is. And humanity nowadays uses SI units based on meters, kilograms, and seconds as the fundamental units that everything else is defined in terms of. I mean, there are a few more, but they are the basic ones. And what I want to talk about is the kilogram. Now, the kilogram is the least satisfactory of the current units. The reason being that the definition of a kilogram since 1889 has been the mass of a particular metal object which is stored very securely in France. It's made of a special platinum-iridium alloy which has got twice the density of lead and is extremely resistant to scratches, because if you were to scratch it you would have changed what we mean by a kilogram. And the question I want to answer in this video is, what is the shape of this piece of metal? What is the shape of the standard kilogram? And to do this, we're going to think a little bit and use some mathematics at the level of calculus, of elementary calculus. And obviously this whole system of saying that a kilogram is the mass of a metal object is not satisfactory, and from May 2019 a brand new definition is going to be brought in which will not refer to the mass of a particular object. So the question that I want to start with first of all is, what is the shape of the standard kilogram? And one of the things that you would ask yourself if you wanted to do this is, which shape has got the minimum area? So which shape has the minimum area for a fixed volume? So you have a particular volume, and that means for your particular alloy, platinum iridium, as I say, in the kilogram that we use, for a fixed volume it's going to give you a fixed mass. So you could imagine lots of different shapes which have got the same total volume and hence the same mass because they're made of the same metal. So which shape, you might then say, has the minimum area, because that way you're going to minimize the risk, no pun intended, of having corrosion, rusting, things being exposed to air. And the answer to that question is a sphere. So a sphere has got the minimum surface area. But the problem with a sphere is that it would roll around. So whenever you moved this object, you took it out of storage, it would move, it would bang into things. That would not be a very good idea. So the shape people chose instead was not a sphere, but it was a cylinder. And by choosing a cylinder like this, which has got a particular height, so let me show the height here, and it has a particular radius here, we can fix the volume, and in this way we can make our object. And this is what people did. They made a cylinder with a particular radius and a particular height, and this is the shape of the standard kilogram. And there are various copies of it around the world. There are copies in the UK, in the US, in very many countries. So what I'm going to do now on the next slide is work out, using mathematics, what the ratio of the radius and the height are. Because you could imagine a cylinder which is quite low so a cylinder like this, or you could imagine a cylinder like this, very tall, with a small radius, and both of these, if you shape things correctly, would have the same volume. So the question is, what is the ratio of R and H that was chosen back in 1889 to be the shape of the standard kilogram? And that's what I'm going to solve on the next slide. So before we can use calculus to work out how to minimize the area of a particular cylinder with a fixed volume, we need to remember a little bit of geometry. So first of all, the volume of a cylinder which has got radius r and height h is pi r squared. That's the area here times the height. So pi r squared h is the volume. The surface area of our cylinder of metal is going to be the area of the top plus the area of the bottom. I'm calling that the area of the ends, plus the area of the side. Now the top and the bottom are circles of radius r, so the area of each of them is going to be pi r squared, so the area of both of them together is 2 pi r squared. So what about the area of the side? And the way to answer that is, imagine that this was a sheet of paper. Just imagine it was a tube and you wanted to work out what the area was. Well, you could always imagine just cutting it down here like this and then unfurling it. And if you unwrapped it, what you would get would be a rectangle. So the rectangle would be like this, and the sides here are where you cut it down here. So this distance is the height h, and this distance along the top is the circumference of the circle that forms the top or bottom of the cylinder, and that circumference is 2 pi r. So if you imagine unfurling your cylinder like this, you can see that you're going to get a rectangle. One side is h, the other side is 2 pi r, where r is this radius, and the area of the rectangle is this length times this length, so the area of the side is going to be 2 pi r h. So therefore the area of the cylinder is 2 pi r squared for the sides plus 2 pi r h for this side here. So this area is 2 pi r h, and the area of the top and the bottom is 2 pi r squared. So this looks initially as though it's a function of two variables, the radius and the height, but if we remember that we're interested in a fixed volume, we're interested in having a piece of metal with a fixed volume and a fixed mass, that means that R and H are related in this way to the volume. So in particular, I can rewrite H in terms of the volume divided by pi r squared. So I can say that pi r squared h is equal to V, divide both sides by pi r squared, h is equal to V divided by pi r squared. So this tells us that the area, the total area, is 2 pi r squared, that's the area of the ends, plus, and then it's going to be 2 pi r times V over pi r squared. The pi on the bottom here and the pi on the top here will cancel. There is an r here and two factors of r on the bottom, so this r will cancel with one of those terms, and what we're going to be left with is the 2 the v and 1 power of r. So we get 2v over r. And this is an expression for the area, the total area, top, bottom and sides of our cylinder of radius r and a fixed volume. So the volume appears here and that's fixed. So now what we're going to do is try to find at what particular value of r this is minimized, and then we can take that value of r, find out the value of h, and understand in that way what is the ratio between r and h. And notice that there is going to be a minimum. If r becomes very small, this term is going to become very big because you'll be dividing by something very small and the volume is fixed. So you'd have the area would be something small for small r plus something very large. On the other hand, if we took the radius and made it very large, this will become small because you've got the fixed volume divided by something big, but this would be big because it's got the r squared factor. So for small r, the area is going to be large because of this term. For large r, the area is going to be large because of this term. And somewhere in the middle, we're expecting a minimum. So let's calculate that on the next slide. So previously, we found this expression for the area in terms of the radius and the volume of our block of metal, our cylinder. And we understood that if we were to plot a graph of the area against the radius, it's going to look something like this, where the area is going to get very large for small r, very large for large r, and in the middle somewhere there's going to be a minimum. At the minimum, the slope of the tangent line is 0. This is called a stationary point, and it's a point where the derivative, which is the slope of the tangent line, the derivative is going to be equal to 0. So what we're going to look for is what is the derivative of a with respect to r. So we differentiate this with respect to r. We pull the 2 in front, we get 4 pi times r. So we have 4 pi r. And then in the second term we have 2v times r to the minus 1. So we bring the power in front, that's minus 2v, reduce the power by 1, so that's r to the minus 2. So we can just write that as minus 2v over r squared. So at the minimum, we expect, or we require, that dA dr is equal to 0. So dA dr is equal to 0. This is a stationary point, and if this is equal to 0, it must be that 4 pi r is equal to 2v over r squared, so that they can cancel. So we're going to have that 4 pi r is equal to 2v over r squared. Now, we are interested in finding the value of r where we have the minimum area. This value of r is not going to be r is equal to 0. So I can multiply both sides by r squared. And if I do that, I'm going to get 4 pi r cubed is 2v. So let's divide both sides by 2. And I'm going to therefore get 4 over 2, which is 2 pi r cubed is equal to v. So at the minimum, this equation links the radius of the cylinder to the fixed volume. But remember, we saw earlier that the volume of the cylinder is pi r squared h, so this tells us that 2 pi r cubed is equal to pi r squared h. So we can cancel here the factor of pi, And we can divide both sides by r squared because we know that the minimum is not when r is equal to 0. So divide by r squared here, and if I take r cubed and I divide it by r squared, I'm going to get r to the power of 1. So this equation becomes 2r is equal to h. And what this means is in the cylinder which was used and it still exists in Paris, the height of, or in Sèvres actually, it's near Paris, the height of the cylinder is equal to twice the radius, but twice the radius is the diameter, which I'll call d. So h is equal to d. And that is the shape of our cylinder. And if you look online, you will find photographs of the standard kilogram, and you will see that they are cylinders whose height is equal to its diameter, and that's been chosen because that is the shape of a cylinder that minimizes its area for a fixed volume. So I hope that's been interesting for you, and with that I'll stop this podcast.